morning. Let me remind you what we did last time. And we actually derived the Euler equations for the perfect fluid. I can say slightly ahead of myself that it's not a complete equation which is used in hydrodynamics because it neglects friction effects. In fact, we will learn about the Navier-Stokes equations, which takes into account friction. But these are, in many cases, you can treat the fluid as inviscid. In other cases, you cannot. Actually, it depends on the problem and actually on the domain. When you have a flow, some parts of the flow, viscosity is important, some part it is not. Actually, people joked that Euler equation described the flow of dry water. But in fact, they're very useful, nevertheless. Okay, so the equations are density, the alpha dot, alpha is 1, 2, 3. This is a derivative, this is basically these two terms is acceleration of the fluid particle, as we discussed last time, and it is equal to the gradient of the pressure. Pressure is assumed to depend in a particular way on the density, unless of course, if the fluid not only inviscid but also incompressible, then density is a constant and pressure is determined in terms of velocity. But typically it's determined from the equation of state. And if we have some other forces, we have to add them also. For instance, we looked at the gravitational force and so on. And the other equation is the continuity equation. The divergence, I remind you my notations, d beta means simply partial derivative with respect to x beta. It's basically a common abbreviation. And this is the continuity equation which expresses the conservation of mass in the fluid. Now, a couple of comments before we go further, which actually I forgot to make these comments last time. The comments concern the symmetries of this equation, general symmetries of this equation. What can you suggest as a symmetry? Symmetry, as always, is just the way of getting new solutions from the old solutions. So what kind of symmetries you can think of when you look at this equation? Suggest something, even if it is obvious, it's okay. Well, the trivial symmetry is the symmetry under rotation here, right? Namely, if you rotate coordinate system, it's a scalar, it's the equation which equates vector to vector. Actually, I think we will put it in the homework. Write down, the problem will be an easy problem, but important, is to write down the transformation of V alpha under rotation. So you have the function, the solution V alpha of x and t, and you are asked to go to another solution obtained by rotation. That's pretty obvious because the presence of such symmetry is obvious because we take scalar products and we take when the equation equates say vectors to vectors or tensors to tensors, that means that it's rotationally invariant. Okay, now something else. Again, don't be afraid of trivialities now. What else we have here? Translation. How would you describe the new solution obtained by translation? Well, that's completely trivial. It's just V alpha of x plus a t. So far it's all easy. Now a slightly more difficult but also an easy symmetry is time reversal. Do we have time reversal here or not? The suspicion should be on the first time derivative, but think a little bit. First of all, think physically whether we expect time reversal, and then explain to me what should I do with V, how to obtain V. So is there time reversal or not? Make an educated guess about it.
I mean, there doesn't appear to be because there's only a single first time derivative, and it's added to a.
Okay, that's a natural reaction, but wrong. But it's fine. If I didn't know the answer, I would probably. That would be the first guess, that because of first time derivative. But okay, the answer is that there is time reversal. Not surprisingly, because we derived it from the Newton equation. But in any case, what shall we do to? It's indeed the first time derivative, so we should do something quite physical, which it's not some tricks or something. So we want to know V alpha of x and t when we reverse time. So when we do the filming backward. What happens to the velocity when you do the filming backward?
Flip sign.
Yes. Two things flip sign here. It's time and velocity. So what would you say? What's the new solution? We still have to look at the other parts of the equation, but I'm now thinking about this one.
Equals negative v.
That's right, yes. Indeed, if you substitute v tilde to this thing will not change. Now, what about this one?
Again, the two negative signs cancel.
Yes, and there's no time here. So that fits. Here also, how about this equation, the continuity equation?
So rho dot becomes negative, and so does.
Yeah, so we have to also take rho of x and t to be rho of x and minus t. When you do it simultaneously, the equation is preserved. So if this satisfies the equation, this satisfies the equation. Okay, density, of course, doesn't change sign when we film backward. Okay, now there's one more extremely important symmetry before we go further here. What we have forgotten to to discuss some important symmetry, which we know it's all symmetries of the Newton equation, because it's just a continuous approximation to the Newton equation which we are dealing with. So time translation, yes, but that's kind of, that's all right, yeah, but we have something in the Newton equation which is more subtle. Well, remember that Newton equation are invariant under change of frame, under Galilean transformation. So we should expect that this equation should be invariant under Galileo transformation. But the question now is what is the alpha tilde? What would you suggest? We have to guess.
Plus a constant.
What?
The alpha plus a constant. Plus a.
Okay, let's try it. Or better to say it's not quite right. Maybe it's more gentle formulas. Anyway, let's try to plug it back to the equation. That's a normal procedure. You guess some new symmetry, check, and it either works or not. But there's nothing to be ashamed of when you get, if it doesn't work, it doesn't work. Okay, so this term is fine, yes? When we add the constant, nothing changes. Now let's do it with this term. When we shift this guy, there is a derivative, so nothing changes. But when we shift this guy, we get non-zero result. You see? So this V tilde does not satisfy this equation. It changes the equation. So what should we, and there is a good physical reason why it happened. Think of really what happens in the frame which moves. Galilean transformation is moving the frame with constant velocity. Now, just visualize what happens. Indeed, when you go to the passing, to the moving frame, you do add this thing. However, your coordinates are not the same. They are shifted by Vt. You see? So what I'm saying is the right answer will be, that's what Galileo does. If you substitute it into the equation, then you will have two terms. One term we already wrote down here, but there will be another term coming from the alpha tilde dot, which will be the alpha dot minus u beta d beta the alpha. And this term will precisely cancel the contribution of this one. So once again, there will be two terms. When you make this substitution, there will be two terms, one coming from the shift of velocity u, and it will give you this term in the equation. And then the other comes from, is it obvious how I got this formula? or not? If it is not, then look, we differentiate with respect to time. And we have time enters into two arguments. We have t here, so we have to differentiate with respect to. So we basically, by definition of the derivative, we take then we expand in delta t, and we have two terms. One is coming from the time derivative, and the other coming from this thing. And you see, it's quite interesting because it tells you, it shows you that nonlinearity, the origin of nonlinearity. If you simply drop this term, then you will not have this physical. You cannot modify the equation by, say, putting some coefficient here. If you put, say, coefficient 1/2 in front of this nonlinear term, you will spoil the symmetry. So it's quite, and actually it's important when discussing turbulence, where things are, as physicists say, renormalize, that there are certain, they renormalize, but they do preserve things like this coefficient, the Galilean symmetric term. Okay, and the last comment on this, so we talk about time reflections. What kind of term, if we add it to the equation, would break time reflection? Just figure out, imagine some correction to the equation which will break time reversibility.
So just a term proportional to the alpha?
Yes, we can get this term proportional to the alpha, and you are right, it will break time symmetry. In fact, in some cases, those terms proportional to the alpha really exist. In fact, they do appear, again running ahead of myself, in expanding universe, for instance. But in a normal fluid, what you get is the term proportional to the Laplacian of the alpha. The term, the reason why the term of the alpha is does not appear. Tell me why in the normal circumstances, when we do not consider expansion of the universe, the term proportional to the alpha cannot appear. There is a symmetry which forbids it. Apart from, we agree to break down a time reversal symmetry, but there is also the other symmetry which we have, which we want to keep. What about Galilean symmetry? It's clearly will be broken because you shift v to v plus u. Okay, so if you want to keep Galilean symmetry, you cannot have the term v alpha, but actually there is a similar term which is allowed. What would be the similar term which is allowed by Galilean symmetry? Something quite simple.
The alpha double dot.
The alpha double dot will, yeah, that's also a possibility, but in fact it contradicts something else. But the typical term which appears which we will be discussing a lot, but you're right, actually that's a correct answer to this question. I probably should have put the question differently. in reality, in real fluid, the term is Laplacian of V alpha, which appears on the right-hand side. And that's the effect of viscosity. That we will be discussing a lot. But now, let's return to the problems which we looked at last time. And the problem was that we looked at the linear approximation. And one interesting problem, so we wrote down rho as rho 0 plus rho 1. So we imagine a gas which is homogeneous, and then we perturb it a little bit. Rho 0 is a constant, and rho 1 depends on x and t. Okay, it depends on x and t, and V alpha, and we assume that this term is much smaller than this one, and V alpha is also a small term, and so this will be the second order smallness, V is proportional to V square, and we left, we looked at the equation rho 0, V alpha dot. We dropped this term. We introduced an important constant, which is compressibility, and at the same time, it turns out to be speed of sound. So with c squared d alpha rho 1. Plus, we said when we looked at the gravitational case, we had the gradient of the gravitational potential multiplied by rho 0. So the problem which we looked at was that we originally have completely homogeneous distribution, constant density. We assume that there is self-gravity in this gas, that different, if you have a certain point, a certain fluid particle, it is subjected to the gravitational attraction from all other particles. And when things are infinite and then gravitational attraction in all directions is the same, it's an equilibrium, because the particle is not dragged anywhere. But we saw that when we solve this equation, and of course we have to also to deal with the continuity equation. So once again, and of course we have to deal with the equation which determines the gravitational potential, which is just, we can actually write down it, avoid writing down by writing the integral, but it's more convenient to. So we assume that the gravitational potential was 0 originally. It's quite clear that this equilibrium is unstable, because if you make, we discussed it already, if you make fluctuation of density, it will be attracting particles. Without it, we have just, without gravity, we saw that the solution is, the general solution of this equation for the density is the following. It is a of k e to the ikx minus omega of kt plus complex conjugate. That with or without gravity, we have this form of the solution, and omega of k, it's dependence, it's sometimes called the dispersion relation. K is a wave vector, and for sound, without gravity. We also noticed that the linear formula is good if velocities which are of the same type. So velocities, or I put it, yeah, 0. Velocities are determined by the initial condition, and they must be small in comparison with the speed of sound. Actually, I thought a little bit, I gave you an explanation how it is possible that all fluid particles move with small velocity, much less than sound, and nevertheless we transmit information. I think I shall partly repeat it, partly modify the explanation a little bit. If you have an eraser and you move it just a tiny distance, and suppose you are sending the signal from here and receiving signal here, the fact that it moves by some distance delta x in time delta t, that's the velocity of its particles, right? But the speed of sound will be not delta x, but the length of the eraser divided by delta t, because you will feel you will receive information at the distance L and receive it in the moment in time past delta t. So that explains how, well, there's nothing much, but just small clarification that there's two different velocities moving of the fluid particles and speed with which transformation is transmitted. But maybe it's it was unnecessary. Probably the analogy with spreading rumors was much better than this detailed explanation.
Sorry, what does the eraser represent in that case?
What?
What does the eraser represent in your example?
Well, eraser is my fluid. So it's not a very good idea, but the eraser is collection. Imagine it's a collection of fluid particles, although it's not, because it's solid. And then I push it just a little bit, and I receive information in time delta t. I receive information on the other end. Information means you know that I pushed it. At the same time, velocity of constituent particles here, they are very small. They can be made as small as I want.
So the eraser is somehow being pushed at a velocity much faster than whatever is pushing it?
Well, it's practically immediately transfers your push to the other side. You see, that's the point. Okay, that there are two very different scales at which. And you can see the same thing here, because the crest of the wave moves with speed of sound if omega is ck, while the velocity of the fluid particle is determined by completely independent quantity, this initial condition. So it's quite obvious here. Okay. One important and omega of k we said is c square k square minus 4p gn rho 0. Gn is the Newton constant. And notice one interesting thing that I probably will write it more explicitly as a star e to the minus akx e to the plus I omega kt. That's the solution of the equation. As we said, it's, the general solution is obtained by taking arbitrary linear combination of these solutions. This is solution corresponding to a particular wavelength k, or wave vector k. Now I want to ask you the question. What are the symmetry reasons for two? We make two observations here. First is that we have exponential dependence on time. And second, that we have two exponents, this and this, in the general solution. I want to hear symmetry explanation. It's both facts are related to symmetry. Which symmetry? Let's start with the exponential. That's something which we discussed. There's nothing very new and not really. So why it's exponential? Why we looked for the exponential solution? Say in harmonic oscillator. It's basically harmonic system of harmonic. Yeah, go ahead. Yes, it's because it is the solution. The equation is time translation invariant, and so we expect that when we translate time, we get a new solution. And indeed, if you just translate time, you get overall coefficient, but the function. So I'm talking about the relation, which is just an arbitrary constant. And it's all that we discussed. It's always the case with translation symmetry, where be it in time or in space. These exponentials here is a result of spatial translation invariance that we discussed. And now something which we didn't very much discuss. Why we have two exponentials here? Try to figure out which symmetry is responsible for these two exponentials.
Translation in space?
Well, in space, forget about set x to 0. Forget about x dependence. I want you to concentrate on time. It's time reversal. You see, if we have only one exponential, then the solution with reverse time will not be a solution. So it's inevitable that you have two exponential e to the minus I omega t and e to the plus I omega t, and that's extremely important for our case, because of this time translation symmetry. See what happens then. K, so we introduce the Jeans wavelength. And when k is less than kj, omega of k is equal to I absolute value of omega of k. I will call it I gamma of k. All right, and then when I substitute it, I will get the fluctuation of density. It will contain some a of k. Again, these amplitudes are determined by initial conditions in the problem. E to the, say, plus gamma of kt plus another b of k e to the minus gamma of kt. And we have both unstable solution, the blow up of density, and exponentially converging solution. That's absolutely unavoidable because of time reversal symmetry. However, and that's very, now listen because it's very general and important point. When you observe those fluctuations of density, you observe at very large time, you observe exponential growth only. The reason is that your devices have finite precision. It's always the logic in statistical physics. They are able to detect only with finite precision fluctuation of density. Now, what they will see for large enough time, they will see the growth of this density, and when it drops beyond resolution power of your device, this thing will be unobservable. So, as a result, you will have an illusion that you are dealing with time asymmetric situation. And that's precisely the illusion we have in statistical mechanics, that the entropy grows and its time translation asymmetric. At the same time, the Newton equation are time asymmetric under time reversal, and that created a tension between the two. And the answer in general I discussed with you already the growth of entropy because of spreading of in the phase space. Here it's much simpler and very explicit. You just have imaginary frequency, and that's it. You get inevitably you get this blow-up solution, and that's an instability. By the way, when you discuss sound with viscosity, when you take into account that's a digression from the main theme. If you add to the Navier-Stokes equation the term as we will the Laplacian d alpha, now it becomes the Navier-Stokes equation. Before it was the Euler equation. So if you do this propagation and you study, of course it's very easy to study propagation of sound here. Again, you linearize, you solve, it's literally the same calculation, but this term will give you some extra contribution. You will get, you can just in fact, it will be some other constant, or something else, but it's all doesn't concern me. I want to write down some coefficient A multiplied by k squared, and it will come with imaginary thing. So the frequency will be imaginary again, and that's why the sound, why we have the sound which goes down. Now, why I can't argue that in this case, what I'm trying to say is that in the case of sound in a viscous fluid, you also have imaginary frequency, but it's a different imaginary frequency. It describes only damping of sound. It does not describe the blow-up. Why? What's the principal difference between gravitational instability, which we are dealing here, and the propagation of sound in viscous gas?
So you lost time reversal symmetry when you added low cost.
Exactly, and that's why I will have I will have the solutions. It's easy to check from here that the fluctuation of density with damping it contains ICK, let's set x equals 0, CK T plus some C1, C2, e to the minus I c kt. That's the answer for without viscosity, and there will be overall e to the minus some coefficient gamma k square. And as you see, this solution is explicitly not time reversal because multiplied by t, excuse me, because of this last term. You will never get the blow-up term from this. That's because this is a solution of the equation which breaks time reversal, while the gravitational instability is a solution of the equation which preserves time reversal. Now, there is one more interesting example which I'm going to discuss, which is related to expanding universe, and also to these galaxy formations. But I just want you to appreciate that this simple formula explains to you why we see apparent around us we see apparent violation of time reversal. And its origin is basically this, that you're simply unable to observe the time reversal side. Okay. Now one more interesting solution. As I told you, by the way, that this Jeans instability, it's instability in the sense that we get a. I should have said this. It is an instability because we got exponential blow up of this, but of course. We cannot say whether it will be a real blow up or not. Why is that? What are limitations of this formula? Remember what we conjectured when we derived what approximation we made when we derived this formula. Yes, but if v is exponentially growing, at some moment of time it will not be true anymore. Initially it was much less than c, but then you can use this formula only up to a point, or the point where v is of the order of c. And then you have to solve the full nonlinear problem. We will be discussing this. It can, in some part of these nonlinear problems can be solved. Other parts are not. And it's believed in general that this exponential instability is responsible for formation of galaxies. The only difference is that you have to write down basically the same equation. It's interesting that general relativity leads to basically the same equations. Except that these equations are now written in the context of expanding universe. And what do you think will happen with this blow-up? Will it be stronger or weaker? It's weaker, yes. Actually, you can give some simple hand-waving argument that it will not be exponential, but the power-like growth. And indeed, there are two conflicting things. One is that the universe is expanding, it tends to dilute the gas. On the other hand, we still have a gravitational attraction, and that leads to a smaller instability. Actually, people believe, that's funny, that in 1950s, people believed that because of this relatively weak instability, that it's not enough to form galaxies, but it was just a prejudice. In modern physics, we believe that Jeans instability is the origin of structure in the universe. And what is also, I think, quite philosophically interesting is that how simple it is to derive this so fundamental thing. I put it this way, that to build up hydrodynamic theory of scrambled eggs, is much more difficult than create a theory of the universe. That's strange. That happens. That fundamental problems are often simpler than concrete, small, everyday problems. Okay. Now one more solutions which we will discuss. And that's exactly relates to expanding universe. Let's imagine that we have some kind of dust, and this cloud of dust expands, and we want to write down the corresponding equations. We will write down the equation rho v alpha dot plus v beta d beta v alpha, and it should be equal to, we will neglect the pressure. It's actually not necessary, but it's a good approximation in many cases. For some stages of the universe, well, I will not go into this, but at certain stages you can neglect the pressure when you have really heavy objects, kind of dust. And what we want to put on the right-hand side is the force. This is the acceleration of the fluid particle. We want to put the force which acts on this fluid particle. And because of symmetry, this force is just Newton constant multiplied by the mass of this thing divided by and I guess that's it, yes. So with a minus, because it's attracted. And and of course we have to multiply it by rho, the mass of the test particle we are putting here. And the mass here is the mass of the whole universe. So the mass here is equal to rho multiplied by 4 pi divided by 3 x to the cube. So the force which you put to the right-hand side of the Euler equation will be just 4 pi divided by 3. Did I erase it? Well, that's fine. The Newton constant, the rho, the x to the cube will cancel, and we will have x here, x alpha here. And we also, rho goes away from this. Let me write down the equation. The alpha dot it is actually rho square here, so I was wrong to say this. V alpha dot plus V beta d beta V alpha is equal to 4 pi divided by 3 gn rho x alpha. and rho dot plus d alpha rho v alpha is equal to 0. So we have this system of equations describing the expanding ball of dust, which, however, self-gravitate. So each particle in the ball is... and the density of this ball is, of course, time-dependent. And we have to figure out what can we say about V alpha. And usually when you have such equation, you have to try, as people say, the Ansatz, the German word for substitution or something, and try to find the right ansatz for those V alphas. So what would you think would be in what form we want to look for the solution V alpha of x and t? What kind of guess we have to make and then check whether it goes through the equation, consistent with the equation? How velocities, you have expansion, how velocities are naturally directed. In this, imagine the box, this ball of dust, and well, you see, if you try this and that, you will end up with the following equation. We have some constant, which a function of t, multiplied by x alpha. We have to guess the reason why we should be hopeful that it makes sense is that it is a rotationally invariant ansatz. It's invariant under rotation of x and v simultaneously. So we must hope that it will not give you inconsistency with the equation. So let's check it. It is actually not difficult at all. It's amazing. I'm just deriving for you the equation of expanding universe. It's amazing how simple they are, and that the fact that they are confirmed by many facts is quite fascinating. All right, so V alpha dot is simply h x alpha. Now, if we take V beta, T beta, V alpha, we have h square. It's h dot x alpha. Okay, we have h square. We have x beta, d beta, x alpha. Okay, and so we get h square x alpha from this. See? So our Euler equation for the universe becomes very simple. The first equation becomes simply h dot. H, by the way, is called the Hubble constant. It shows that in this expanding universe, the velocity of some point at the distance x from the observer runs away with the proportional to the distance. And that's what Hubble discovered astronomically using his telescope. So, all right, we have h plus h square equal to the density, we will assume simultaneously that the density is just a function of t. And now we have to work with the, actually I believe it should be a plus, that we have to figure out by looking at the solution, either following the equation carefully or, yeah, there was a minus, there was a plus here because there was a minus for the gradient of the potential. Anyway, we will see. Now, with the continuity equation, we have the first term, which is rho dot. Now we have the second term, which is this. And this is simply 3h rho, and it's equal to 0. So now we have a very simple system of differential equations, which we will solve. And this system of equations have some remarkable consequences, actually. First of all, the meaning of this equation is very simple. It is just the, you can always integrate it and express rho in terms of h. For instance, suppose for one moment it's inconsistent with this one, but that h is a constant. Then what will be the meaning of this? What will be the solution and its meaning?
Rho decays exponentially.
The what?
Rho decays exponentially if h is constant.
It will be e to the minus 3ht, yes. What does it mean? It means simply that universe expands, the density getting smaller and smaller. It dilutes. So it's very, for a time-dependent h, the meaning is the same, basically. Just the formula is somewhat different. Now, how to solve this equation? First of all, we have to determine how h depends on t. And it's clear that these two terms should be of the same order. So make some guess of how h, concerning the solution, how h depends on t. What would be a reasonable thing to try?
1 over t.
Yes, because then two terms are of the same order. So let's try h of t, some constant a divided by t. Then rho of t, we should look at, suggest something for the rho of t. What would, if we want to keep all terms of the same order?
1 over t squared.
Yes. So let's. And now things are very simple because you just have a square from here minus a from here is 4 pi gn divided by 3 multiplied by b. And here we will get also a quite simple result, minus 2b plus 3ab is equal to 0. So we conclude that a should be equal to 2/3. And you calculate b from this thing. And you'll find that b is that we find that well, if it's 2/3, you get 4/9 minus 2/3 minus 6/9. So, okay, I think I will not be doing this arithmetics because I will make a mistake anyway. But what I want you to say is that we obtained the density law in terms of, if you know the Newton constant, all these constants are known. Okay? And that leads to a remarkable prediction, which is the basis of the our theory of the early universe. The prediction is that, well, first of all, it's easy for you to believe, I guess, is that the density in the Newton approximation becomes energy density in the relativistic theory. It's surprising that Einstein equation leads to the same equations. It's the same thing, precisely, except that rho is not mass density but energy density. Okay? What can you say in this case about the temperature of the universe? The universe cools off. How it will cool off? I want to know the temperature. Remember some physical law which will determine the temperature. Suppose that at we're at very high temperatures and we have radiation mostly. What is the law of radiation which we can use here? How the energy density of radiation depends. You have a black body. How the energy of radiation depends on temperature. Imagine you have a hot black body in a box, and then there's thermodynamic equilibrium. And then you have in the equilibrium some constant temperature, and the energy depends on temperature. Actually, there's a Stefan-Boltzmann law which solves this, which tells you that energy is proportional to T to the 4th, and as a result, you know, it's some known constant divided by square root of time. And so this is time 0 is the moment of the Big Bang, and probably our formulas are not applicable at them too close to the Big Bang, but then it's certainly applicable when we have time to establish thermodynamic equilibrium. Universe expands and the temperature goes down by this thing, and the thermal history of the universe is derived in a very simple way. You just say when the temperature, say, of the order of drops below, say, the nucleon mass, then the nucleon masses go out of equilibrium, they freeze up, and so you finally you reach the temperature at which electrons recombine with protons, form atoms, and so on. The universe becomes transparent. And all this, it's all subtle and a lot of interesting intellectual achievements related to this. But they all are based on the fact that this constant is known. That's quite wonderful that there's no free parameters here. It's just expressed in terms of the Newton constant. Okay, so that was the example, our first example of nonlinear solution of the Euler equation. Let's now discuss the nonlinear sound. We will be developing. The most interesting part of hydrodynamics is, of course, nonlinear phenomena. In linear approximations, roughly speaking, all equations look the same. And in the nonlinear, it's a different story. But and while we have general methods for solving linear problems, it's far from true in the nonlinear cases. But there are some great achievements there. Okay, so let's try to solve the problem of sound without making this conjecture concerning linearity, concerning small perturbations. By the way, before I go to this, a question. So we have these equations, and they have a solution. How would you approach the problem of galaxy formation? What should you do if you are interested in galaxy? This is strictly isotropic universe, which we are describing here. Homogeneous and isotropic. And we want to get structure from, and suppose you still work with the Euler equation, which people really do actually, because they are working in many cases, in many special problems. They give the same result as Einstein. Okay, but what I'm asking, just general approach. What if you want to see? We already discussed that there is some instability which is responsible for the galaxy formation, and how to what to write, what formulas to write. Imagine you sit at your desk in the morning and you have somebody ordered you to derive the formula for galaxy formation. What would you start with? Yes, please.
Make an infinite series of solutions with varying mass.
Yeah, but that's true. We actually will have to take, we have a particular V alpha and rho, which is V alpha of t in this case, which is actually h of t x alpha, and rho, which is rho of t. And we have to perturb it with some fluctuations of v and rho, which depend on both x and t. And the reason why it is a relatively simple problem is that we will linearize the equation as we did before with Jeans instability. And so before, when we discussed Jeans instability, we linearized the equation assuming rho is a constant, assuming the universe is static, not expanding. Here we will do the same thing. We will consider, so for instance, we will consider rho of t plus rho 1 of x and t. We will take V alpha of x and t, which is h of t x alpha, plus delta V alpha of x and t. Delta V alpha is a small perturbation of velocity. And then we will write linear equation. And that's, I'm not going to do this, it will take too much time. But the answer will be that we will still have Jeans instability, except that it will be power-like growth, not exponential growth. But so I want you to understand the principle, how you approach this problem. All right. Now we will switch. We will go to the to another example of nonlinear problem. And as I said, it deals with it deals with sound. And we will write it down for one-dimensional sound. Actually, the general nonlinear sound, no, it's impossible to solve analytically. But for in one, if you have time and one-dimensional space, or in our three-dimensional space, if you consider a wave which is propagating in some z direction, then you can really proceed, you can develop the technique and get some physically interesting result, which I'm going to do. So I will write down the equation, as I will use this, it's another notation. It's time derivative plus dvx and we have this equation, and we have the equation so these are the system of nonlinear equation describing describing propagation of perturbation in one dimensions. Now, it's not possible to solve them in general, even in one dimension, but you can find a huge class of spatial solutions, which are very important physically. And as a first step, I will simplify, we will return to the equation after we learned something about them in a simplified limit. That's again is a general strategy when you deal with complicated problems. Simplify, try to first solve some toy problem which is with drastic simplification or something like that. Namely, I will look at the case first, then pressure is zero. Pressure is a function of rho in general, and let's suppose that we are in the circumstances then which happens indeed when the pressure is practically zero. It corresponds to which speed of sound, by the way? If we say that the pressure is zero, what we assume about the speed of sound? Yes?
It's centrally charged.
No, it's the other way around. If you have the sound propagates because there is pressure, you compress things and then they resist compression. If you have no pressure, it keeps going. There is no. So the sound, it's the limit when the sound is tends to zero, actually. The speed of sound tends to zero. And in this case, we have a very simple equation for which we can find an explicit solution. And this is such equation, such partial differential equation are actually solvable in general. There is maybe I shall mention a little later the general method for solving the equation where here you have an arbitrary function and so on. But let's solve this particular one first. So once again, this class of equation with one unknown function, partial differential equation of this type, are solvable, and you will see why. when you have more than one variable, there is no general method for solving them. But there are some special solutions. Okay, let's write down the equation in this term. Let's take it dt. So let me write it down. dd dt dd dx is equal to minus v, which depends on x and t. Now, what do you think? Try something bold with this form of equation, and then we'll... When you have this, what should your instinct tell you when you look at such an expression? The what?
Cancel the...
Yeah, something. The instinct should tell you something totally crazy, but partly correct. So naively, you would think that there is something like, let's cancel this dv in the numerator with the dv in the whatever it means, and then you will get dx dt. That's the wrong answer, but pretty close to the right one. And it's much better to get this wrong answer than not to get any answer at all. Oh, well, we're running out of time. So the right answer is the following. Here we differentiated at constant x. Here we differentiated at constant t. So we have the function v of x and t. And we also can take x as a function of t and v. When you have, so what I'm saying is we have the function v, which depends on x and t. We can invert this equation and solve it for x. And a very simple property which I will show you is this, that if we have dv dt at constant x, dv dx at constant t, it is equal to dx dt at constant v. And the only difference with the naive answer is that there is a minus here. There is a minus, and it also specifies what kind of differentiation, what this formula means. Probably will do it next time. But I want you to appreciate what it means. It means that you can actually simplify the equation drastically. You simply have some first derivative of some guy which is equal to v. And next time I shall derive this formula, which is very simple. It's just one of the properties of implicit functions when you invert function. By this we will solve the equation. Okay, let us stop here.